All right, chapter 3, derivatives, something a little more computational and a little bit less theoretical for you. So in this chapter, we'll use limits. So we're certainly not done with limits, but maybe we can set aside some of the epsilon delta type stuff for a while. But we'll apply limits to define the derivative of a function. The derivative is related to the instantaneous rate of change that we introduced in section 2.1. And we'll derive a bunch of rules about differentiation. We'll apply derivatives to rate of change problems, something called related rates. And again, this is a bit more computational and giving you a little break from the more rigorous theoretical stuff. Okay, section 3.1, tangent lines and the derivative at a point. So we'll define the slope of a curve in this section, and we'll take inspiration from some of that stuff from section 2.1 about secant lines and tangent lines to define inspiration for defining what we mean by the slope of a curve. Okay, and this book's taking the angle that the whole reason for doing limits was for the following, at this stage at least, and that's why they made such a big deal about secant lines and rates of change in section 2.1. So we're defining the slope of a curve, y equals f of x, at a point, x sub 0, f of x sub 0, a point on the graph of that curve, to be the number m equals a limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 over h, assuming that limit exists, provided that limit exists. The tangent line to the curve at this point is the line through point P with these coordinates that has this slope m. Okay, so this is all coming to us inspired by something we really dealt with in section 2.1. So this is figure 3.1. The only difference in this and what was done in 2.1 is I think we've modified the x sub 0, or we've modified what was c there to an x sub 0 here. We certainly did things very similar to this in section 2.1. So what we're doing is we're looking for the slope of this red tangent line. Effectively, that's what we're calling the rate of change, or the slope of the curve, which we'll also refer to as rate of change and slope of tangent lines, but we're calling it the slope of the curve, and it's going to equal the slope of this tangent line. So what we'll do, as we did in section 2.1, is we'll pick 2 points, P and Q, that both lie on this graph of y equals f of x, and the idea is we'll make P and Q close together so that the slope of the secant line through those 2 points will be close to the slope of the tangent line. For the sake of a picture, let's suppose P and Q are this close together. So we can actually see the picture. So we've taken the point x sub 0 and the point x sub 0 plus h. Now h in that limit approached 0. Could be h is negative and that point Q lies somewhere over here and the picture's somewhat different. But for the sake of a picture, let's in the picture assume that h is greater than 0, and the idea is h is small. Then we've gone a distance h to the right. We can find slopes then by doing a rise over run thing. The rise, the difference in the function values, is whatever function value we have here, f of x sub 0, where that was the input, and whatever function value we have here. The input's x sub 0 plus h, so the function value here is f of x sub 0 plus h. So here's the 2 points, the coordinates of P and Q. P, x sub 0, f of x sub 0, Q, x sub 0 plus h, f of x sub 0 plus h. So to find the slope, we'll take the rise over the run. The rise would be, say, f of x sub 0 plus h, this y value, minus f of x sub 0, the y value down here, the distance from here to here, technically measured along the y-axis, divided by, rise over run, the distance from here to here. And we've chose that to be a distance of h. If you like, it's x sub 0 plus h minus x sub 0, which simplifies down to h. We hinted at some of that in section 2.1. So the slope of this secant line would be f of x of 0 plus h minus f of x, rise, divided by h, run. The slope of that secant line would be this little part here. Forget the limit stuff. So there's the slope of the secant line. Now, if we take a limit as h approaches 0, then that secant line becomes arbitrarily close to that tangent line, assuming the limit exists. And in the limit, the secant line will have a slope that becomes, in the limit, the slope of the tangent line. So the definition should make sense at this stage because of the way we set things up in section 2.1 and because of the way we've treated limits. So definition of slope of a curve is given as that particular limit. Let's go through and illustrate it. There'll be some redundance in what we're about to do, carefully following the verbiage of the book. Let's go through and find the slope of a curve as given here. Okay, find an equation of the tangent line to the curve, y equals 2 square root of x, at the point 1, 2, then sketch the curve and the tangent line together. You good at graphing square root functions? It's half of a parabola. Arguably, you're not that good at graphing just yet. You will be. You'll be good as anybody else once we get through Calculus 1. You know how to graph some special functions. You know how to graph lines. You know how to graph parabolas. This is a graph of half of a parabola. You've been exposed to the square root function before, no doubt. You know how to graph conic sections, maybe. You're good at graphing polynomials. Well, you will be by the time we get through applications of this differentiation stuff to graphing. Then you'll be as good as graphing as anybody else. All right, so here's what we need to do. They want to know equation of the line tangent to the curve. Okay, that'll be a line that has the same slope as the slope of this curve at the point 1, 2. So we've taken f of x to be 2 on the square root of 2. We've got the point in the symbols of that definition, x sub 0, f of x sub 0. We've got the point 1, 2. X sub 0 was 1 in particular. So the slope of the curve, y equals f of x, is m equals, limit as h approaches 0, f of x sub 0 plus h minus f of x sub 0 over h. That was the definition. Here the function is 2 square root of x, so we'll put x sub 0 plus h in for x, getting 2 square root of 1 plus h, x sub 0 is 1. F of x sub 0 would be 2 square root of 1, x sub 0 is still 1, divided by h. Let's clean it up if we can. That's not much, but getting rid of that square root of 1 there. And we're left with 2 square root of 1 plus h minus 2 over h. We want to evaluate that limit. At this stage, you know what to do. We'll multiply by the conjugate. So we'll change this negative to a positive, divide this thing by itself, multiply by that. That's 1. Any concerns over square roots and negatives? Could 1 plus h be negative? No, h is close to 0. So the square root of 1 plus h is close to the square root of 1. For h sufficiently close to 0, we don't have any concerns over square roots and negatives. Okay, let's distribute. All right, distributing and foiling in the numerator. First outer inner last, we'll get the square of the first minus the square of the second. That's why we multiplied by what we multiplied by. That gets rid of the square roots in the numerator. Yeah, well, it introduced them in the denominator, but we can deal with that. So we'll get the first squared, that's 4 times 1 plus h, 4 times 1 plus h. Second squared, it's just 2 squared, it's 4. Nothing I can do about the denominator just yet. Here we've got a 4 minus 4. So those cancel out, and we're left with a 4h in the numerator. Okay, this is where we left off on the previous slide. We got a 4h in the numerator. Oh, we got an h in the denominator as well. Can you just cancel those h's in a limit? Yeah. In a non-limit, well, as long as h doesn't equal 0, we were just doing algebra stuff, not calculus stuff. if h is not 0, then you could cancel the h's. We did write h doesn't equal 0. We wrote it when we wrote limit as h approaches 0. Remember, it doesn't matter what happens at 0. So you're totally justified in canceling those h's. This goes back to our first conversation in chapter 2. So though the functions are different, the limits are the same. We'll speed up our computations of limits in this chapter a little bit. Now, let's see. Can you plug in h equals 0 and nothing goes wrong? If we plugged in h equals 0, we'd get a square root of 1, and we get divided by 4. So, yeah, nothing went wrong, which is a shortcut way of saying the hypotheses of theorem 2.1, theorem 2.2, and possibly theorem 2.3 involving rational functions. I mean, we're applying those theorems. As long as nothing goes wrong informally, we can do these limits by substitution. Square roots and negatives would be a problem. We're not getting square roots and negatives when h is little. More formally, we've taken the limit of the quotients. Then we took the sum rule to get the limit of the first and the second. Possibly we brought a 2 outside. I didn't include that in my list, but maybe we use the constant multiple rule. And then we got the limit underneath that square root using the root rule. That's the big step. And then we substitute in based on the fact that 1 plus h is a polynomial. So there's all the technical reasons that we can evaluate this limit by substitution. You're good with the technical stuff after chapter 1. So happy maybe now to streamline this a little bit and not put in all those intermediate steps. And when we simplify, it looks like we get 1. 4 divided by 4. Yeah, we get 1 out. All right, so 1 is the slope of the line. Tangent line has slope 1. We were given that it passed through the point 1, 2. That was the point we were given, x sub 0, y sub 0, I think we called it. Let me use the symbols x1, y1. Because we usually state the point slope formula as y minus y1 equals mx minus x1. Anyhow, the x and y values that go here from the point are these x and y values. We got the slope as 1. So if we'll substitute that stuff in, we get y minus 2 equals 1, the slope, x minus 1, that one right there. Multiplying out, that's y minus 2 equals x minus 1. Bring the 2 to the other side. That's y equals x plus 1. So there's the formula for the line. Here's the slope of the curve and the slope of the line. Here's the formula of the tangent line. At that point, let's draw a picture because they asked for that too. Square root function, 2 times the square root function, will produce this blue curve. You plug in 0, get out 0, plug in 1, get out 2 times the square root of 1, get out 2, plug in 4, get 2 times the square root of 4 is 2 times 2 is 4, plug in 9, so forth, get out 6. Plotting points is not a good way to graph unless they're special points or unless you already know what the shape of the graph is. I do know the shape of the graph. It's a half of a parabola. Square root functions are half of parabolas. So I do know the graph looks something quite similar to this. Now the line, y equals x plus 1, great at graphing lines. You got a point. We had the point 1, 2, right? And we knew the slope was 1. This is the line. So here's a graph of the function we were given. Here's a graph of the line tangent to that function at x equals 1. And the geometry looks pretty good. So the picture looks like it's right. Let's do another one. Okay, basically the same type of problem, different function. And they didn't ask for a graph, they just asked for an equation this time. Find the slope of the graph of the function f of x equals x minus 2x squared at the point 1, comma, negative 1. Then find an equation for the line tangent to the graph there, that is at that point. Can you graph x minus 2x squared? I suspect you can, or you've been exposed to it at least. It's an opening downward parabola. Quadratics, x squares type functions. Second degree polynomials have graphs that are parabolas, and you know how to find the vertex and the axis and that kind of thing, probably. They didn't ask us to graph it, but I suspect you got a pretty good idea how to graph such a thing. So in your mind, you know what to visualize. Now here, It's the calculus we're mostly worried about. We got the function, x minus 2x squared, and we got the point 1, negative 1. You want the slope of the curve? That's the limit as h approaches 0, f of x of 0 plus h minus f of x of 0 over h. All right, so we'll plug into f, x of 0 plus h. X of 0 is 1. So we'll replace the x with a 1 plus h here and here. 1 plus h minus 2 times 1 plus h squared, because the function is x minus 2x squared. Wherever you see an x, put a 1 plus h. Now, wherever you see an x, put an x of 0 to get this part. Oh yeah, x of 0 was 1. So we'll put a 1 there and there. We get 1 minus 2 times 1 squared. Don't forget to subtract. Don't forget to put the parentheses here, because we're going to work this limit by factoring, canceling, and substituting. You mess up the arithmetic, you won't be able to factor, you won't be able to cancel. Something will go wrong if you mess up the arithmetic. Be very careful to include these parentheses here and get the signs right. Okay, so let's see, that's 1 plus h minus 2. 1 plus h squared is 1 plus 2h plus h squared, multiplied out. Here we've got 2 minus 2 is negative 1. Keep that in those parentheses, minus a negative 1 here. Let's distribute the negative 2. So we get the 1 plus h to come down. Negative 2 times 1, let's give us negative 4h minus 2h squared, negative minus 1 is a plus 1, and some stuff cancels. If it doesn't cancel, then something's wrong. The 1 here, the 1 here, and the negative 2 here cancel. So we lose the 1, the negative 2, and the 1, add up to 0. We get an h and a minus 4h. Do the arithmetic there, leave you with a negative 3h, and we still got the minus 2h squared. Okay, can you factor? Factor what? Well, it's the h in the denominator that's bugging us, because h approaches 0. So we need to cancel that h. We'll then factor an h out of the numerator. So here's the factor step. Factor the h out, leaving you with a negative 3 minus 2h, negative 3 minus 2h. Can you cancel those h's? Of course you can. It's a limit. So let's speed that up a little bit. That leaves you with negative 3 minus 2 times h. Can you substitute the h in? Of course you can. Why? It's a polynomial in h. And we get negative 3 out. So we've got a slope of negative 3 and the point 1, negative 1. They want an equation for the tangent line. I think we're good to go. We got a point and a slope. Slope is negative 3, point is 1, negative 1. Point slope formula is still y minus y sub 1 equals m, x minus x sub 1. Here's the x1, y1. The slope m is negative 3. Substitute those in. Simplify and distribute. Rearrange it maybe to read y equals. There's a unique form of a line if it's written as a function, y equals mx plus b. If I leave it in these other forms, it is the line, but there's multiple ways to represent lines if you don't put them in this form. So here's the equation of the line tangent to the curve. It's got the correct slope. Yeah, it's got a slope of negative 3, just like the curve does at that point, as we saw in the previous slide, and it passes through the point 1, negative 1. You plug in x equals 1, you'll get out negative 3 plus 2, negative 1. You'll get out the appropriate y value. So that is indeed correct. Okay. A very slightly new definition. I warned you about some redundance. The expression f of x sub 0 plus h minus f of x sub 0 over h, where h is not 0, is called the difference quotient. The difference quotient of f at x sub 0 with increment h. We'll mention difference quotients a bit. They'll be useful when we use these things, and maybe the x and y values have units like miles per hour, and these are going to be rates of change. So I'd expect miles per hour to be the kind of thing we might see. We're defining here the derivative of a function at a point x sub 0. In the previous definition, I mean, we had the same thing. In the previous definition, we called it the slope of the curve. So what we're doing is taking the slope of the curve basically, and calling it the derivative at a point. So the derivative of a function f at a point x sub 0 is the same thing we had above. Limit as h approaches 0 of the difference quotient, since we gave that a name, assuming the limit exists. All right, so you can take derivatives at points. Let's do that. In an example, all right, find an equation for the straight line having slope 1/4 that is tangent to the curve y equals the square root of x. Okay, well, let's find the derivative of y equals f of x equals the square root of x at point x sub 0. We know that'll give us the slope of the curve at that point, and they want straight line having slope 1/4 that is tangent to the curve. So we'll want the slope of the curve, which equals the slope of a tangent line at various points. We'll want the slope of the curve to equal 1/4. So we'll set the derivative, which we're about to compute, to the desired slope of 1/4, and that's how we'll figure out where we need this line to be tangent to the curve. That's how we'll find the x sub 0. And once we have the x sub 0, we'll be in business to find a y sub 0 and then find the equation of the line. We'll have a point and they gave us a slope. So the mystery here isn't the slope of this line. The slope's 1/4. The mystery is what point does it pass through? And they've given you that information fairly indirectly. Okay, so derivative, y equals f of x, square root of x at a point. It's the limit of the difference quotient. Substitute in the x sub 0 plus h for x, and then substitute in the x sub 0 for x. I don't know what x sub is. That's the point. I'm looking for a value of x sub 0. Multiply by the conjugate when you see these square root things. That's becoming routine at this stage. Distribute, multiply out in the numerator, FOIL it. You get the first squared minus the last squared. That's why you did this. That produces an x sub 0 plus h and an x sub 0 and a difference. The square roots are gone in the numerator. You're stuck with them in the denominator. The point is to factor, cancel, substitute. Okay, here's where we left off on the previous slide. We can cancel the x sub 0s. X sub 0 minus x sub 0 leaves us with this. Cancel, maybe not the best teaching word to use in this part. The cancellation comes now. It's the h in the denominator that's kind of causing the trouble. We've set up a situation here. Actually, we got it factored. You've got h times something on the numerator, and you got h times something in the denominator. It's h times 1 in the numerator. So the factoring has been done at this stage. Now we can do the cancellation and cancel those h's because it's a limit. And can you plug in h equals 0? Yeah, by the sum rule, the quotient rule, and the root rule. If you want the details, really, you can plug in the 0 if nothing goes wrong. You're getting square roots and negatives. X sub 0 can't be negative. It was in the domain of the function. So x sub 0 isn't negative, no problems there. X sub 0 plus 0 is not negative. You're not having problems with negatives here. So like I said, we'll start to streamline the evaluation of the limits a little bit. So we've got a square root of x sub 0 plus a square root of x sub 0 in the denominator. That's 1/2 times the square root of x sub 0. So this is the slope of the curve at various points at point x sub 0. So we want to figure out which x sub 0 makes the slope of the curve equal to the slope 1/4. That is, we'll have a straight line with this slope that's tangent to the curve. Well, where does the curve have slope 1/4? We'll set 1/4 equal to this thing here, 1/2 on the square root of x sub 0. I won't bore you with the details. Quite obviously, we need that square root of x sub 0 to be 2. That is, we need x sub 0 to be 4. So this will happen when x sub 0 equals 4. All right. They want a line. We've got a slope for the line, and we've got an x coordinate for a point on that line. We still need a y coordinate. All right, so the desired line's got slope 1/4, passes through the point x sub 0, f of x sub 0. It'll be tangent to the curve x sub 0 equals 4. On the curve, what's the corresponding y value? So I simply plugged 4 into the original function, square root of x, the original function, square root of x, not this thing here, that's the derivative. We're looking for a point on the curve y equals f of x, square root of x. So we'll take the square root of 4, and that gives us a 0.42. This is the point we'll use in the point slope formula. Your best friend on this stuff is probably the point slope formula, because you're going to get slopes from derivatives and you're going to get points algebraically. So point slope formula tells us y minus y1 equals mx minus x1. M, the slope, is 1/4. We had that from the beginning. And now we know x1, y1 are 4, 2. Plug the 4 in for x1, plug the 2 in for y1. Simplify, it looks like we'll get y equals x over 4 plus 1. Got a slope of 1/4, like it should. If I plug in 4 for x here, sure enough, we'll get out y equals 2. So it passes through the appropriate point. It has the correct slope. That's the line. Okay, so that wasn't that different from the derivative stuff we were doing. Okay, derivative of a function at a point is a limit of an average rate of change. That's how we inspired this stuff in section 2.1. So we see that the derivative can be interpreted as an instantaneous rate of change of the function f with respect to the variable x. To make it more physical, and you'll use this in physics a bunch, talking about positions and velocities and accelerations eventually. If f of t is the position of a particle at time t, so the input variable is t, then the instantaneous rate of change of position with respect to time, in other words, the instantaneous velocity at time t equals t sub 0 is f prime of t sub 0, computed the usual way. Limit as h approaches 0 of the difference quotient, except we're using t's instead of x's this time. So you're thinking of derivatives as velocity functions. Provided f of t is a position function, more of that. I mean, this is a big deal. You're going to use this a bunch. So this is the first time we've seen a representation of position as a function, but it ain't the last. So f of t is position, f prime of t is instantaneous velocity. Let's illustrate that. Okay, at t seconds after liftoff, the height of a rocket is 3t squared feet. How fast is the rocket climbing 10 seconds after liftoff? Okay, so they're measuring t in seconds and they're measuring height in feet. I will be conscientious of units. In a math course, it's maybe tradition to be a little loose with the units. Yeah, we shouldn't, because the physics folks and the engineering folks are going to depend on you to keep up with units. So I got a little bit of a physics background and a tiny bit of engineering background. So I'll be quite conscientious with the units on this stuff. So feet and seconds, fast. Well, they're going to be the units of fast, of a velocity. It must be here, must be feet per second. So we'll keep an eye on that too. Okay, instantaneous velocity is, by definition, it's this limit. Limit as h approaches 0 of the difference quotient. Okay, the function we're dealing with here is an elementary function. It's a height function, f of t equals 3t squared. So f of t sub 0 plus h would be 3t sub 0 plus h squared. F of t sub 0 would be 3t sub 0 squared. That gets us set up. No square roots, so no worries about multiplying by conjugates this time around. We get the h in the denominator. And I might start out at the beginning saying, can you plug an h? No, because that'd give you division by 0. We'll set it up like this. Can you plug an h? No, because you get division by 0. Let's multiply the t sub 0 plus h out. So that'll give us a t sub 0 squared plus twice the product, t sub 0 h plus h squared. You got a 3 out front. Simplify the notation a little bit on the right-hand side. Can you plug an h now? No. Okay, let's distribute the 3. Distribution. I get some stuff that'll cancel. The 3t sub 0 squared and the negative 3t sub 0, I can eliminate those to produce this. Can you plug the h in now? No, because there's an h in the denominator. Let's factor the h out of the numerator because we can. There's the factor in factor cancel substitute. Can you plug the h in now? No. Can you cancel the h's? Yeah, because h is not 0. I wrote it right there. When we wrote limit as h approaches 0, that means h is close to 0 and not 0. So cancellation is valid. The functions are different. The limits are the same, as I commented somewhere in chapter 2. Can you plug in the h now? Yeah. Why? Because we got a polynomial function. Actually, we got a linear function. Its graph is a line in terms of h. I don't know what t sub 0 is. The answer will have t sub 0 in it. But h gets close to 0. This quantity will get close to 6t sub 0 plus 3 times 0. You can evaluate the limit by substitution because it's a polynomial. Theorem 2.2. Use it so much I remember the number and the name. And this reduces down to 6t sub 0. What will the units be? Feet per second. Where'd that come from? Look back up here. F is height. Height's measured in feet. H, we got t sub 0 plus h. H is a little slice of time. Think of it like that. So h is measured in seconds. So we've got feet divided by seconds. We've got, I don't know, this many feet divided by that many seconds. But the units are feet per second, as it should be. It's a velocity. So we've got f prime of t, the instantaneous velocity at time t sub 0. They want to know how fast the rocket is climbing 10 seconds after liftoff. That is when t sub 0 equals 10. So we'll plug in t sub 0 equals 10 into this velocity function, and we'll get 60 feet per second. I may not keep up with the units throughout the computations, but I'll certainly put them in at the end of the computations. It's pretty ugly keeping up with them along the way, but I will be conscientious of units and keep up with them. It's a velocity, feet per second. Yeah, that sounds right. So there's using derivatives to find velocity functions. As time goes by, that velocity is going to get bigger and bigger. So the rocket's going faster and faster. Yeah, it's accelerating. Is what's happening. And we'll talk about acceleration here shortly as well. Okay, so we've treated the derivative in a number of ways. We have several interpretations of the limit of the difference quotient as given here, either as a slope of the graph, y equals f of x at x equals x sub 0, slope of the tangent line, rate of change, instantaneous rate of change of f with respect to x at x sub 0, or the derivative f prime of x sub 0. So that one idea has had several different names is because it's so useful, turns out. One other little topic here that pops up really, it's almost a side topic, but we've talked about slopes of curves and slopes of tangent lines. We're good to go unless we have a vertical tangent line. What's the slope of a vertical line? This should sound familiar from your high school experience. Vertical lines have undefined slope or no slope. I don't even know if the term no slope is still in vogue. It sounds too much like slope 0. Undefined slope is better. Vertical lines have undefined slope. But I could still have vertical tangent lines. Well, what would happen in that case in terms of all this derivative stuff? Well, something could go wrong with the derivative. So we're going to define for a continuous function, f of x, a vertical tangent line at point x sub 0, provided the two-sided limit of the difference quotient is either positive infinity or negative infinity, two-sided limit. So it's one of these two, not maybe positive from one side and negative from the other. The two-sided limit is positive infinity or negative infinity. And we get a behavior of a function that looks something like this. This is the cube root function, y equals x to the 1/3. And indeed, it's nice and continuous. And at 0, it has a vertical tangent, which makes sense. I mean, the y-axis is tangent to the curve at the origin. You can verify algebraically, limit-wise, calculus-wise, you can verify that the limit as h approaches 0 of the difference quotient equals infinity for this function. Straightforward computation. Possibly it's an example in the book. Got this picture from somewhere. Or maybe it's an exercise. But you can confirm that this function has a vertical tangent at 0. Let's illustrate that with an example. Like in this section, it's significantly shorter than some of these recent ones we did, where we're asked the question, does the graph of f of x equals x to the 3/5 have a vertical tangent line at the origin? Okay, well, first off, if you plug 0 in, you get 0 out, so it really does pass through the origin. Do you know what the graph of this function looks like? You might have some insight on it. If I knew what the graph looked like, I could probably quickly answer this function, or answer this question about the vertical tangent thing. So if you don't know much about the graph, and I could certainly believe that's the case, then, well, you're learning something about it. You're learning some weird behavior about it at the origin, at x equals 0, y equals 0. Okay, so, well, let's look at what they were just talking about. Let's look at a limit of the difference quotient as h approaches 0. The function is x to the 3/5, so we'll have 0 plus h to the 3/5, minus f of 0, x of 0 is 0 in this one, minus f of 0 divided by h. Can you plug in h equals 0? No, probably can't in this one because I'm expecting to get an infinite limit out. All right, so that leaves us with h to the 3/5 over h. Okay, that disappeared. Well, that's just 0. We lost the h. The 0 plus here just leave us with an h. Okay, let's see. We got division of here with powers of h. Subtract exponents. We could write this a couple of different ways. Let's write it as 1 over h to the 2/5 power. Limit as h approaches 0, 1 over h to the 2/5 power. Can you plug in h equals 0? No, you'll get division by 0. Well, let's see what the numerator and denominator does. The numerator is just 1, so it has a limit of 1 as h approaches 0. The important thing here is the numerator doesn't go to 0, goes to 1. Denominator goes to 0. Can you substitute h equals 0 into this? Anything go wrong? I don't think so. You got any square roots and negatives going on here? No, we're taking fifth roots. We're squaring fifth roots. That's what a 2/5 power means. So yeah, we got no problems with this stuff. We've got the function defined. In fact, the function's greater than or equal to 0. The squaring makes it greater than or equal to 0. And we take fifth roots. There's no concerns over square roots and negatives. So Dr. Bob's infinite limits theorem says you got a numerator that goes to 1 and a denominator that goes to 0. That's going to have an infinite limit. Dr. Bob's infinite limit theorem says infinite limits. We'll have to consider left and right limits potentially. Let's see. Let's check out the signs. We made little sign diagrams for these in the past. The numerator is positive. It does. It's 1 all the time. So the numerator is positive. What about h to the 2/5? Like I said, that the meaning of those symbols is h to the 1/5 squared, or if you like, the fifth root of h. So a typo here. Fifth root of h squared, and that's greater than or equal to 0. So a couple little typos here. Fifth root of h squared, h to the 1/5 is fifth root of h. Whatever that is, you can take fifth roots of all real numbers. So the domain of this would be all real numbers. Square it, and that's going to give you something that's non-negative out. So typo here, conclusion of non-negative is correct, no matter what h is. So if we were to make a sign diagram of 1 over h to the 2/5, The numerator is positive because it's 1, and the denominator is positive as well because we'll stay away from h equals 0. Remember, we're taking a limit. So anyhow, we get positives out. You knew the limit would be plus or minus infinity. The function's positive. Whether h is greater than 0 or less than 0, we could break it into one-sided limits. We don't have to in this case because we know the sign on both sides of 0 is plus. So the limit must be positive infinity. The two-sided limit. The limit as h approaches 0 of 1 over h to the 2/5. This thing here must equal positive infinity for emphasis. And yeah, the graph does have a vertical tangent at the origin. If the two-sided limit had been negative infinity, then we'd be good to go again. It'd still have a vertical tangent. The graph must look somehow different. Actually, let's talk about that one a little bit more. If we were to consider a different function, x to the 4/5, what we'd end up with is a limit as h approaches 0 of 1 over h to the 1/5. Same manipulations that we had upstairs, but you'd end up with not a 1 over h to the, what do we have before, 2/5. You'd end up with a 1 over h to the 1/5. And what you'd see then is the limit as h approaches 0 from the negative side is negative infinity, and the limit as h approaches 0 from the positive side is positive infinity. They're different whether we come from the left or the right. Trust me on this claim. You want justification? Well, all right. Dr. Bob's infinite limit theorem tells you these one-sided limits will be plus or minus infinity. And then I go through and do the little sign diagram on the function. Over here, we've got a positive numerator, and we actually got a negative denominator. That's why we get negative infinity. Over here, positive numerator, positive denominator. H is a little positive number, and that's why we get positive infinity here. So in this case, that's why the limits are what they are. So if we were to graph the x to the 4/5 function, it'd look something like this. The fact that you're taking something and raising it to the 4th power means you ain't going to get negatives out of this one. And in fact, the graph looks something like this. It reminds me of parabolas. These are subtly different shape from parabolas. They're not half parabolas. Parabolas have a specific shape. These remind me of that shape. These are not parabolas, though it turns out. But this is a situation, more of this in the future, where the graph is said to have a cusp at the origin. And if I were to look at tangent lines, let's take the point 0, 0, and a little point over here, and draw a line, a secant line through this point in the origin, it'd be a line with a negative slope. If I were to do the same thing from the other side, take the origin and a point on the curve somewhere close to the origin, we'd get a steep line with a positive slope. So what happens is we approach 0 from the positive side. Those tangent lines keep getting steeper and steeper and steeper with positive slope. That's the reason the limit as h approaches 0 from the positive side is positive infinity. Other side, over here, you take lines closer, take h closer and closer to 0, closer and closer. But you make h small, and you'll get really steep lines with negative slope. And that's the reason you're getting a negative infinity out for the limit as h approaches 0 from the negative side. So when the limits are the same, both positive infinity or both negative infinity, there's a vertical tangent line. When the limits are different, infinite, one negative infinity, one positive infinity, that leads to this cusp behavior. More of that in a future section, but this is why it matters whether we have those limits existing from one side or two. And I think that takes care of, yeah, excellent. That takes care of this section here. So nice short section. As commented, chapter 3, it's more computational. We're going to relax a little bit on taking limits, and I'll still worry a lot about Theorem 2.1 and justifying limits, but not to the level of worry that I had in chapter 2. So we're learning stuff, and we're going to start speeding things up a little bit in terms of computations. I will see you in section 3.2 here shortly, and we'll do more derivative stuff. Have a nice day.